In this episode, we take a step back and do something that sounds abstract, but ends up being one of the most practical security habits you can build. We model the attack surface of an AI system. Attack surface is simply the collection of ways an attacker could interact with your system, influence it, or extract value from it. And for AI, that surface tends to be larger and more layered than beginners expect. It is not just a model behind an endpoint. It is also data pipelines, retrieval sources, memory, agent behaviors, tool connections, authentication, logging, and the integrations that stitch everything together. When you can name the parts of the attack surface clearly, you stop treating AI security like a foggy mystery and start treating it like an engineering problem. The title of this episode mentions 5 big zones: data, the model, agents, tooling, and integrations, and our job is to understand what can go wrong in each zone and why those zones connect. Once you understand those connections, you can make better design decisions, because you will see how a small weakness in one area can become a big breach when it interacts with another. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Data is the first and often the largest part of the attack surface because data is both fuel and output for AI. In many systems, data flows into the model from user prompts, uploaded documents, retrieved knowledge bases, chat history, or telemetry. Each of those paths can carry sensitive information, and each path can carry malicious content designed to manipulate the model. For example, a user prompt might include private identifiers that should not be stored, while an uploaded document might contain hidden instructions meant to override system rules. Retrieved data might include restricted documents if access controls are weak, and chat history might leak across sessions if isolation fails. When you model the data attack surface, you ask where data originates, who can influence it, how it is validated, where it is stored, and who can read it later. Beginners often focus on whether the model is accurate, but the bigger security question is whether the data entering the model is trustworthy and whether the data leaving the model is handled safely. Data is also where privacy lives, so modeling the data surface helps you identify where personal information could leak into logs, analytics, or third-party services. The model itself is part of the attack surface, but it is helpful to treat it as a component with specific behaviors rather than as a magical brain. The model can be abused through crafted inputs, such as prompt injection in LLM systems or adversarial examples in other ML systems. The model can also leak information depending on how it is trained and how it is queried, which includes risks like membership inference and model inversion when sensitive training data is involved. Another model-related exposure is extraction, where an attacker tries to replicate your model's behavior through repeated queries or stolen artifacts. When modeling the model surface, you consider how the model is accessed, what kinds of outputs it provides, and what safety features exist around it. You also consider versioning and update behavior, because changes to the model can change the attack surface by introducing new capabilities or weakening refusals. A beginner misunderstanding is thinking that model risk is only about harmful content. But model risk can also be about privacy leakage, intellectual property theft, and unpredictability under adversarial pressure. Agents are an important attack surface expansion because an agent is not just generating text, it is making decisions about what to do next, often across multiple steps. Even when an agent is simple, it can create a loop where the model reads information, plans an action, calls a tool, reads the result, and repeats. This multi-step behavior introduces new failure modes, because a small manipulation early in the loop can cascade into unauthorized actions or data exposure later. Agents also tend to be more vulnerable to prompt injection because they often ingest untrusted text from external sources as part of their reasoning. If the agent treats that text as instruction rather than data, it may choose unsafe actions. Another agent risk is goal drift, where the agent pursues the wrong objective because the prompt was ambiguous or because the environment includes conflicting instructions. When you model the agent attack surface, you ask what the agent is allowed to do, what it can access, how it decides, and where humans can intervene. You also ask whether the agent has memory across tasks, because persistent memory can create cross-session leakage and can allow attackers to plant long-lived instructions. Tooling is the set of external capabilities the system can use, and it is a major security boundary because tools connect the AI system to real assets. Tools might include search, document retrieval, database queries, ticket updates, message sending, code execution in controlled environments, or workflow triggers. Each tool comes with credentials, permissions, and side effects, which means each tool can be abused if the model is tricked into calling it incorrectly. Tooling also creates risk through the tool outputs, because tools can return untrusted text that feeds back into the model and influences the next step. In other words, tools create both action risk and content risk. Modeling the tooling attack surface involves listing each tool, what it can do, what data it can access, whether it is read-only or write-capable, and what authorization checks occur before a tool call is executed. A strong beginner takeaway is that tools should be treated like privileged helpers, not like toys for the model to play with. The more powerful the tool, the stricter the scope and oversight should be. Integrations are the connectors and pathways that tie the AI system into the rest of the environment, and they often become the hidden attack surface that teams forget. Integrations include identity and access management, logging platforms, data stores, message queues, document repositories, and third-party services. An integration is a boundary crossing, and every boundary crossing is a chance for misconfiguration, overprivilege, or data leakage. For example, if your AI system integrates with a document repository, the integration might use a service account that can see everything, even though individual users should not. If your system integrates with logging, it might send raw prompts into logs that many people can access, creating a privacy risk. If your system integrates with a third-party model endpoint, you might accidentally send sensitive data outside your environment. Modeling integration surface means tracing data flows end to end and asking, at each hop, what is being sent, what is being trusted, and what is being stored. Beginners often underestimate integrations because they feel like plumbing, but in security, plumbing is where leaks happen. Once you have these zones, the real insight comes from the connections between them. Many AI incidents are not a model problem or a tool problem alone. They are chain problems. A user provides input that includes a hidden instruction. The model treats it as authoritative. The agent decides to call a tool. The tool retrieves a restricted document because the integration uses an overprivileged service account, and the model outputs sensitive content to the user. That is a chain crossing all 5 zones: data, model, agent, tooling, and integrations. Modeling attack surface means you practice seeing these chains so you can break them with controls at multiple points. You might break the chain by sanitizing inputs, by enforcing authorization before retrieval, by limiting tool scopes, by requiring approvals for tool actions, and by filtering outputs. You do not rely on one perfect control because single controls fail. You rely on layers because layers make the chain harder to complete. A useful technique for beginners is to ask, for each zone, what are the inputs, what are the outputs, and what assumptions are being made? For data, you ask whether inputs are trusted and whether outputs are stored. For the model, you ask whether it can be influenced by untrusted text and whether it can leak sensitive content. For agents, you ask whether the system can take actions and whether it can be guided into unsafe plans. For tooling, you ask what permissions exist and whether tool outputs can poison the loop. For integrations, you ask whether the connectors honor least privilege and whether data flows leave the environment. This input-output assumption approach works because most security failures are broken assumptions. A team assumes only employees will use the system, then it gets exposed publicly. A team assumes prompts won't contain secrets, then users paste secrets. A team assumes the model will follow system rules, then prompt injection works. Modeling attack surface makes those assumptions explicit so you can defend them or redesign them. Attack surface modeling also helps you decide what to measure and monitor. If you know that the model endpoint is a major entry point, you monitor request volume, refusal rates, and anomalous patterns. If you know that document retrieval is a sensitive boundary, you monitor which repositories are queried and whether requests align with user permissions. If you know that tool calls can cause changes, You monitor tool invocation frequency, success and failure patterns, and unusual sequences of actions. Monitoring is not about spying. It is about detecting when the system is being probed or when it is drifting into unsafe behavior. For AI, monitoring needs to capture enough context to investigate incidents without turning logs into a sensitive data warehouse. Modeling attack surface helps you choose where to place visibility so you can catch chains early before they produce harm. Another benefit of attack surface modeling is that it helps you prioritize controls without trying to secure everything equally. You may not have the time or budget to harden every corner, so you focus on the zones and connections that create the highest risk. For example, a model that only summarizes user-provided text has a smaller surface than an agent that can retrieve documents and trigger workflows. If your system has tool access with right permissions, that is a high-priority surface because it can change records or send messages. If your system processes untrusted files, the file ingestion pipeline becomes a high-priority surface. Prioritization becomes easier when you can visualize the chain. Where can an attacker start, and what can they reach if they succeed? The goal is to reduce the maximum blast radius while also reducing the most likely abuse paths. When you do this well, security becomes a set of deliberate trade-offs rather than a vague sense of unease. As we close, modeling the attack surface across data, model, agent, tooling, and integrations gives you a stable mental map that you can reuse as systems evolve. New features often expand the attack surface, and if you have the map, you will notice the expansion immediately. Adding retrieval expands the data zone and the integration zone. Adding tool access expands tooling and agent risk. Adding memory expands data retention and cross-session risk. Changing vendors changes model behavior and disclosure policies. With the map, you can ask the right questions before you deploy, and you can explain the risk clearly to others without sounding like you are guessing. The strongest beginner takeaway is that AI security is not a single control or a single checklist. It is whole system thinking, where you understand how parts connect and how attacker paths form across those connections. When you model the attack surface intentionally, you are building the foundation for every other control we discuss, because you cannot defend what you have not clearly defined.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.